All right, to reveal what's going on here, I have simulated a completely random example, right? So here I have 100 observations of 5,001 variables. So 5,000 of them are numeric, and they're just independent normal random variables. And the response variable is binary categorical, right? So it's just yes or no. And it is completely random, so which means that no algorithm exists that could predict it better than by guessing, right? So the test error should be just always 0.5. So this is the true test error. Okay, now, so what is going to happen if we actually try to do this cross-validation procedure, right? So first, I'm going to identify variables that are most highly correlated with the output, right? So, and there are, well, two variables. And these are these two variables. So they are, well, they do not have proper names, so just numbers. So the correlation is about 0.3 in both cases. So if we want to use both of them as predictors, right? So our reduced data looks like we just selected these two variables and the response variable, right? And then we're going to construct logistic regression that uses these two variables to predict y, right? So, and you can guess that the true test, the true accuracy should not be more than 0.5, right? At the same time, if we apply the cross-validation procedure for this logistic regression, then we are going to get a ridiculous estimate, right? So that the accuracy is about 68%, right? So which just doesn't make sense. Even though we used proper cross-validation. So the cross-validation procedure here is legit, is good. So the problem was with variable selection. And more specifically, so we used a 5-fold cross-validation. So within these 5 folds, so I have checked it carefully by hand. So these are the error rates. So the average error rate is 0.31, right? So it just doesn't make sense. It is nonsense. So what is the right way to use cross-validation? So can we somehow use cross-validation for variable selection? And the answer is yes, we can, although it is probably not the most common technique. So today we're going to learn better techniques, but we can use cross-validation. So, and by the way, this mistake, so when we first select before splitting our data, before doing any cross-validation, so we just select variables by looking at correlation coefficients with the response, this mistake actually occurs in practice. So beware of this and be careful. So if we want to apply cross-validation for variable selection, it means the following thing. So it means that we have our data, right? So we split it into our 5 folds. And then, so we are going to run 5 iterations of the process. So, right, so every time, so let's say on iteration 2, so we're going to use folds 1, 3, 4, and 5. But now, not to construct, not just to construct our model, but we are going to look at, so we're going to select just folds 1, 3, 4, and 5. So then we're going to choose the most correlated with the response variable on those folds, right? So on the combination, on the union of folds 1, 3, 4, and 5. And these variables that are most highly correlated with the response happen to be these two. Happen to be these two, V166 and V728. All right, and then we're going to construct a logistic regression with these two as predictors, and we are going to apply it, this logistic regression, on fault 2. Yeah. So, and the error here is the error rate of the logistic regression that uses these two variables as predictors, trained on faults 1, 3, 4, and 5, and applied to fault 2, right? And then we do it for every fault, and the mean error here happens to be much more reasonable, is even below 50%. And at the same time, what we see is that every time we do this, so for every fold, so in every iteration of the procedure, the most highly correlated with the response variables are different, right? So it just tells us that there is no consistency here, and everything is just happens by pure chance. So this is how we see the fact that no variable here appears twice, and they're all just different. So it tells us that this is completely random. Okay, so that's the end of the second part of the lecture.